myself Dharini, Assistant Professor, PG and Research Department of Mathematics, the Standard for us Rajaratnam College for Women, Sivakasi. In this session, we are going to see about the limit points of a set and the dense set. In this video, we will be discussing about the limit point and their examples and some theorem based on limit points. Next, we will be moving to the topic dense set and their examples. First, we will be seeing the definition of limit point. We consider a metric space M and a subset A, and we consider a point X belongs to M, and X is called a limit point if every open ball with center X contain at least one point of A which is different from X. In mathematical notation, we refer to it as B of X comma R intersection A minus X should not be equal to empty for all r greater than 0. The limit point is also known as cluster point or accumulation point. The set of all limit point of a set A is a derived set of A, and it is denoted by D of A. Now, let us see an example for a limit point. Now, we consider the set A which is equal 1, 1 by 2, 1 by 3 etc. up to 1 by n. Now, we are going to find the limit point of this set A. Now, we consider open ball minus r comma r with center 0. We are going to choose a positive integer n such that 1 by n is less than r. From the choice of n, 1 by n must be belongs to minus r comma r. Therefore, minus r comma r, that is our open ball, contains a point of A which is different from 0. Therefore, 0 is our limit point of A. We are repeating this step for the 1, but 1 is not a limit point of A, because for the open ball 1 minus 1 by 4 and 1 plus 1 by 4 intersection A minus 1 will be equal to empty. That is, the open ball 3 by 4 and 5 by 4 intersection 1 A minus 1 will be equal to empty. Therefore, 1 is not the limit point of the set A. Now we will be moving to our theorem. We consider a metric space M and we consider the subset A, and X is a limit point of A if and only if each open ball with center X contain an infinite number of points of A. So, we assume X be the limit point. Now, we are going to assume the contradiction that an open ball B of X comma R contains only finite number of points of A. So, we are describing our open ball as B of X comma R. So, intersection with A minus X will be equal to some finite points x1, x2 etc. up to xn. Now, we define S as minimum of distance between x comma xi, where I is equal to 1 to n. Since x is not equal to xi and distance between x and xi is greater than 0 for all I, S must be greater than 0. Therefore, B of x comma open ball of x comma S intersection A minus x must be equal to empty set. By this, we can conclude that S is not a limit point, but we have assumed S is a limit point, so which is a contradiction. Therefore, each open ball with center X must contains an infinite number of points of A. So, conversely, if each ball contains infinite number of points of A, then obviously X is a limit point of A. Next, we move on to the theorem where M is a metric space and A is a subset of M, and A is closed if and only if A contain all its limit points. Before proving this theorem, we see about two lemmas, and A is closed if and only if A is equal A closure. And second lemma, if for M metric space and A is a subset of M, A closure is equal to the A union derived set of A, that is D of A. So, we are going to prove the main theorem. A is closed if and only if A is equal A closure. This is by lemma 1. So, since A is equal to A closure, I can write A is equal A union derived set of A, that is D of A by lemma 2. So, from this we can say D of A is a subset of A. So, the D of A is nothing but the set of all limit points of A. Therefore, A is closed if and only if A contains all its limit point. Next, we move on to the dense set. So, here we are going to see the space M is said to be dense or everywhere dense in M if A closure is equal M, and every point of dense set is a limit point. Definition: a metric space M is said to be separable if there exists a countable dense subset in M. Now, we are seeing an example for a set and its complement or dense in R. So, I am the set of rational numbers Q. Since any open ball B of x comma R contains infinite number of rational and irrational numbers in R, Q closure is equal to R, and also Q complement closure is also equal to R. Hence, Q and Q complement are dense in R. Next, we are going to see the example for separable space. We are considering the R with usual metric. Since we already see the Q closure is equal to R, so Q is dense in R. Also, Q is a countable set. Therefore, R is separable. Next, we will be seeing an example for a set that is not dense. So, we consider a metric with discrete metric space and consider a proper subset of M. So, A be a proper subset of M and A not equal to M. Since A is closed, A closure must be equal to A, and also therefore, A closure not equal to M. Therefore, A is not dense. For a set to be dense, A closure must be equal to M. Here A closure is not equal to M, therefore, A is not our dense set. Hence, from this example we can conclude any uncountable discrete metric space is not separable. Thank you.